Okay, so yeah, so I realized that when I was recording at the church, I had blanked out on the stuff on the T antigen. That was the next part that I was going to get into, so I decided to take a few minutes and review that. And so now I'm back in my room on my computer. Yeah, I'll go over this here instead. It should be the same thing. One thing is I have a really loud keyboard. It's a mechanical keyboard. It helps me with gaming and with typing. I like to write in my free time and so forth. So hopefully the noise won't bother you. But yeah, I was going to say, with the T antigen, so with the T antigen, we're going to go over the biochemical activity. So we've already said that the large T antigen binds viral DNA. And it specifically binds p53. And so when you bind p53 with T antigen, you basically you decrease apoptosis and you allow the virus to multiply more in the cell. So that's one thing that T antigen does. It also T antigen also binds it can bind to 3 different sites on the viral DNA. Those 3 sites are called sites 1, 2, and 3. Site 1 is bound preferentially more than site 2, and site 2 is bound preferentially more than site 3. So when T antigen binds to site 2, then you also bind viral DNA replication. Something else about T antigen. Okay, so write this down. Binding at site 2 results in activation of viral DNA replication. Something else about T antigen is that it is actually a negative. It's like an autoregulator. So when you make some T antigen, you prevent more T antigen from being made. Specifically inhibits the early transcription of the T antigen genes. And the reason why you do this is because you only need so much T antigen to drive the cell towards to drive the cell into S phase and to cell growth, right? You don't want to make more T antigen than necessary. So. Let me pull this, zoom in on this a bit. There you go. I'll maybe zoom out one. There you go. That should be good. So that's bullet point Roman numeral 7. So the next bullet point, 8. Bullet point 8 is DNA replication. So keep saying this over and over again, but just to drill the point home, happens in the nucleus. It's bidirectional, just like our own DNA. There are leading strands and lagging strands, and it exploits cell machinery. and late gene expression. Here, yes. So pause it, copy that if you need to. Maybe I'll zoom out a bit. Late gene expression. So this happens after DNA replication. So this is really important to note in that, remember, SV40 has early genes and has late genes. The early genes code for T antigens, which drive the cell towards DNA synthesis and protein synthesis. The late genes code for the capsid proteins. So you want late gene expression after the DNA replication occurs, because then you can take the thousands upon thousands of newly synthesized DNA and transcribe those, and then you can make a bunch of capsid proteins, and those capsid proteins will go back inside the nucleus, and now you have a bunch of DNA, thousands upon thousands of DNA flowing around, viral DNA flowing around, thousands upon thousands of newly made capsid proteins. What do you do with them? Put two and two together, you form virion particles. Obviously, exploits cell RNA. Yeah, the creation of capsid proteins happens only in permissive cells. So SV40 will only make these capsid proteins if it infected a monkey virus. If it's in a non-permissive cells, like as in if SV40 infected rodent cells, then you would get tumor cells. You won't synthesize any virion particles. You would just transform the cell. And finally, you have assembly of the virus. So permissive cells, you have viral release. Non-permissive cells, you have tumors. So that was pretty much the last part of the previous video that I didn't get around to recording, so I'll merge this one with the previous part. And yeah, good luck with studying. Thank you for watching.